All right, I have set it to start recording. Okay, um, starting over, did the mounting, did the imports. All right, so we're shuffling the data set. Like Israel said, it's useful to do that because we don't want the neural network to learn from the order of things, the order of the data points. So we just see like, we kind of knock off one leg. And there's other ways to test how well a model does. Some things include dropout regularization, which means you chuck out neurons and you see if the model was relying too heavily on one neuron to think about the image. And those are just some techniques we use to make sure the model is learning the way it should. All right, so we're loading it in. And the number of total images is the full data set. We're testing each of the models we have in this folder on the full data set. Batch size is 32, image size. So this is the data cleaning because this came in as raw data. We're not gonna walk you through it in detail, but if you want the detailed stuff, it's here in the project file. We're gonna clean, did I clean it? Hang on. I think I did. Okay. All right, so I'm gonna let's start with, I forgot which of mine was like a good performing one, but I'm gonna probably try the one that says my name. I'm just gonna try to see like how mine did. Obviously, the more time you spend with it, the better your hyperparameters are gonna be for the job. So what this is doing, this is model.evaluate, which is basically Keris's function for testing a model. All right, we're testing it on the whole data set, so it's going to take a second, but not that long. Today's just kind of meant to be light because like we're in the middle of midterms and yeah, there's a lot of panic going around. Okay, so that is the confusion matrix. Does anyone want to remind us what true positive, false positive? Okay, one each. Can someone tell me what true positive means?
This scenario said that it had malaria, and that was correct.
Perfect. So it predicted positive, which means it had malaria, and the answer was that it did have malaria, so it was true. Perfect. Vrindal, I'll get to your question in a second. Does anyone want to tell me what false positive means?
It predicted that it was gonna test positive, right, but it didn't.
Right. Perfect. False negative, anyone? Anyone else? I'm trying to get as many people as possible to answer. False negative. Just go by the logic of true positive. True means it was correct, and positive means it guessed positive. So what could false negative mean? Okay, it means false. False means it was wrong. The guess was wrong, and negative means it guessed negative, meaning it guessed that malaria wasn't there in that cell. And then true negative means it guessed correctly that there was no malaria in the cell. It was a true guess that was negative. So those are the four boxes of the four, I guess, classes of answers you can get in a confusion matrix. All right. Quick rundown through performance metrics. These are important because the confusion matrix, if you notice, there's two numbers we have in this one. One is an actual number, 13,085. That means out of the 27,000 something images, this model guessed 13,085 of them as positive, and those guesses were correct. Same goes for negative, and these guesses were correct. And these two classes were incorrect guesses. So it's always good to have your trues high and your falses low. Are we good so far? Does anyone have any confusion with the confusion matrix? aptly titled. I have half a mind to like turn on some ambient jazz to rid us of the awkward silence. Okay.
Good idea.
You know what? Let's do it. Did I put 3 Z's? Oops.
Yeah, you did.
Wait, let me screen share with audio. Today's chill, so. All right. So performance metrics, there's many of them, right? And we need multiple ways to measure how well a model performs, because it's not enough to just like get accuracy and say, oh good, my model's done, because of the way that these ratios work. For instance, accuracy is represented by the true positives and the true negatives, which means the correct guesses divided by all the guesses. And it's good for like an overall estimate of how well your model is doing, but there are some problems where we want to be more specific. We're looking for a certain characteristic in the model. Dang, I can't take this seriously. All right, so performance metrics are often derived from the confusion matrix, right? This is what we have. It's the same thing. These are the definitions. This is a good link. I can share it with you guys. These are the definitions of the 4 classes. That's all right. So now we have a new metric called precision, and that means we're predicting what percentage of the guesses were truly positive, which means out of the positive guesses, how many were true positives. In this case, hang on, I didn't run it. Hang on. All right. The precision for this model, the accuracy was 95%, 95.4%. Precision was 95.8. Where do we use precision? When we want the false negatives to be minimized. Can someone tell me why it's okay, you know what? We'll come to that. We'll come back to that. But just know that these are just different ratios you can pull out from the confusion matrix. One sec. Where is recall? Yep. Another metric is recall. We're only doing 4 today. Recall is when you have true positives divided by true positive and false negative. And we're basically checking how many were predicted positive. I mean, it sounds weird, but you're going to see why we rely on these specific ones. F1 score is like, in math, they call it the harmonic mean of precision and recall, which I think is a cool title. But can someone tell me if we want can someone tell me if false positives or false negatives are more dangerous in this scenario?
I think that false negatives probably.
Why?
Because like if somebody has malaria and you tell them, hey, you don't have malaria, then they go out into the world and they could spread it to a lot more people. Whereas if you say, hey, you do have malaria, you just can't quarantine them for a week or 2 or something like that. That's
literally it. The stakes are much lower for saying a false positive as opposed to a false negative. False negative means you're letting someone with the disease slip by. Okay, I'm gonna reduce the music volume. Is that better? Okay, right. So that's correct. We want to avoid false negatives. So the metric that's most relevant for us to get look at in this case would be the recall, which right now seems to be decent, 95, almost 94.9. Because like I spent quite some time tuning this model, all of these look pretty similar, but I'm sure like different configurations are going to get different numbers. F1 score, again, it's a math formula. This is more useful when we have a data set that isn't balanced. What balanced means is if we have an unequal number of yeses and nos. In this case, in the case of malaria, we have an equal number of ones and zeros, and that just makes it easier for the model to learn better. But if the model is being trained on data that has a bias, right? And this usually happens in like things like face recognition or emotion recognition. People of a certain demographic are used in the building of the data set, and that usually causes the model's predictions to be biased because data with a bias goes in, predictions with a bias come out. And that's usually a problem. So you want to make your data as even and as fair as possible. When you don't have an even balanced data set, we rely on something called the F1 score, which kind of balances out the previous two metrics that we had. So that's just like a really high level intro to performance metrics. And now what we're going to do is load in each group's model that we have so far, and we will welcome them to show us their model. Actually, you know what? Let's have them show their model first, and then we can get to testing their model. Can group one screen share? Do you guys have the permission to screen share? Hang on, I got it. Okay, while we hang on, I mean, yeah, I mean, it's recorded. While we hang on, Vrindal had a question. Did we set hyperparameters before? I thought we were doing that today. No, when you built the model, you already set the hyperparameters, but you can always go back and change them to increase like the accuracy and now all these other metrics that we have. But basically, hyperparameter tuning is not the same as setting, because setting you have to do the first time. And you would have already done that if your model works. So you did set hyperparameters if your model has been working so far. And after today's test, you guys are welcome to go back. If like the project is kind of done, but we're just walking you through like the more contextual aspect. Israel, whenever you're ready, screen share so that you can walk us through.
Oh yeah, I'm trying to pull it up, but
Sure.
like I didn't bookmark it.
Oh no,
so.
that's fine. You can usually find it if you go to your drive, and there's going to be a little folder that says Colab Notebooks. That's where it's gonna be. Does anyone have any other questions so far? I'm gonna reveal my model at the end because that's gonna be like gonna build up the suspense.
All right, I found it.
Awesome.
All right, how's that look? Oh, let me go to the top.
That looks great.
Where should I start?
You can just head down to the model. Yeah. Oh,
Okay.
wait. Hang on. Where are your layers?
Huh. Yeah, that's weird. I don't know.
All right.
It just disappeared.
Okay. Did you happen to note down your configuration or anything?
I think I did. Yeah. I think I put like ReLU and I used 2 layers and each layer had 20 neurons.
Okay. Pretty
Yeah.
cool. And do you want to tell us what optimizer you used and?
Oh yeah. Oh, it's here. There it is.
That's strange. Do you have like 2 code blocks that say the model?
Yeah, I do.
Interesting. All right, that's fine. All right.
But yeah.
20,
Oh, I have
20,
3.
ReLU.
I have 3.
Nice.
Okay. Nice. Yeah. All right.
All right.
Yeah, so I used RMS prop. Yeah, I think that works the best.
Mhm.
So, but like whenever, like sometimes when I like reload my neural network with a add a delta
Mhm.
or any other one, like it switches around, and like
Right.
the results don't stay exactly the same. So this was kind of like luck, I would say.
Right.
But in this case, like it was pretty consistent. I don't know. I don't understand how it worked. So, but yeah, this worked best.
Right. Um, well, that's great. Do you want to just show us your loss and how much it was in the first
Oh,
epoch and
the
last?
training loss. Yeah, it's
Yeah.
so the lowest it got to is 0.18, and
Mhm.
the final epoch was 0.19. Yeah, that's the lowest I can get it.
Does anyone want to guess why models can increase loss after a while? Isaac, I mean, I'm so sorry. Israel, not Isaac, my bad. Do you have a guess as to like why your model might have increased in loss?
Less number of data to train on.
Could you repeat that?
Less number of data to train on.
Less data to train on. How would that increase the loss?
It's not learning. It's not learning anything new.
Well, I mean, it's learning the same data again and again. If there's less data over 5 epochs, it would have had, it would have gone through that tiny data set quite a few times. So,
Yeah, I don't even know, to be honest.
right. Well, one common reason is because models, especially like in neural networks, they tend to do something called overfitting, which is basically learning too much about the data, as opposed to learning a general rule that lets them classify things accurately. They start learning the data itself, and that's when like you're memorizing the textbook instead of like actually learning the concepts. This doesn't seem like a bad change in loss, though. There's nothing to worry about. But sometimes things go from like now 0.18, they can go back up to like 0.25 or something. It just depends on how the model architecture has been built. Great. Okay. I'm gonna put your model in and let's see how it performs.
Yeah, that's my test right there.
Right. Your test loss was 0.21. Okay.
So it increased.
Right. Remember, here the test data was just 30% of the data set. And in the testing file that I have right now, we're basically testing it on a shuffled version of the whole data set. Okay, I'm gonna stop your screen sharing so that I can run your model on the full data set shuffled.
All right.
Okay. I have changed your group number in. All right, I had to do one copy just because that's the only way that it would let me load the model in, but let's see how it does. So this is this is being tested on both seen and unseen data. It's just been shuffled around. Okay, your precision is super high. And that's good because that means your model is able to avoid false positives. But again, as we discussed, today's, this project, like the most important number for us is false negatives because that's the most dangerous kind of case where you don't tell someone they have, wait a second. Am I mixing them up? False positive? Which one did we say we wanted to avoid?
False negative, yeah.
We wanted to avoid false negatives, right? So that means recall should, I mean, this is not bad by any means, right? Nine out of 10 people are still going to be told the right thing, but that's pretty good. That's a solid model. I think we can move on to the next group. Do we have anyone from group 2 here today?
It's just me, but
Okay.
it didn't save our last model, so the loss is like 69% or something like that.
Okay, that's fine though. This would be the last model that was saved, like after running the whole thing. Like when you run it, it automatically runs that cell where it saves it, which is down here, the cell. So you're saying your final model didn't save?
Well, the one that had the lowest loss, like the
Didn't
one
save.
that I'm currently running is like 69%, but the other
Okay.
one was a lot better.
That's fine though. At least we can just try to see the last saved version. We can try to see what its performance is. All right, 2 copy is yes. Okay. That's a super low loss. That's like super,
Yeah, that's
super low.
different from the one that I have on my page.
You're saying this is the one that was your best model?
Yeah, probably.
Right.
How did he set up the model? Or how did you set it?
Should we do that first, or should we just examine the results and then head in?
Oh yeah,
I
we
mean,
could
I'm
look at
fine
it
either
both.
way.
Let's check the metrics and then we can move into. You have a really good false negative and false positive. Those are like super low. Let's see your numbers. All right, your recall is very high, 0.96. That's awesome, 0.97 really. And your accuracy on the whole data set is above 95%. I believe group 1's was also really accurate, but the recall was slightly lower. But this is great. Do you want to show us your model?
Is it available on the page you have pulled up?
No, because like that's going to be saved in your individual drive.
Oh,
If you don't want to pull it up, that's totally cool.
I can show you what's currently there, but I don't think that's the same model that was shown on your screen.
Do you remember it?
I mean, it had 3 layers, I believe, and then 2 of them had 10 neurons and 1 had 7 neurons.
All right. Okay, so you were like pretty scarce. I'm not sure, but you weren't trying to like overload it with a ton of neurons. You were trying to see like a higher number of layers with a lower number of neurons. Is that kind of what you were trying to use?
Yeah, I guess.
All right. Do you remember your optimizer? Because that usually makes a huge difference.
What are the options for the optimizer?
I can show you that. Hang on. Stochastic gradient descent, root mean square propagation, atom, adaptive movement.
Oh, yeah, I think it was Atom.
Atom, okay. Let's see. Yeah, usually, especially for like classification problems like these, RMS and Atom do a great job. These two are like, before Atom, I believe RMS was the best one, and then they invented Atom. Understanding how these exactly work is going to take some in-depth calculus, so you're welcome to like look into it, but I don't think for now it's in our scope. Sumrat is stepping in. All right, so cool. What else do we have? Group 3, let's check yours out. Is there anyone from Group 3 here? You know what, maybe I should pull up like the groups and check. It's probably a better idea. All right, do we have Casey, Michael, or Ethan today? All right, no problem. Do we have anyone from Group 5? Because I see that's the next model. We have Vivek.
Yeah,
Do you want to show us your model, Vivek?
sure. Okay. So for the actual model, I was kind of trying to get like the number of parameters down. So I did a couple of pooling layers, and then I think that's 4 layers of actual neurons. Because I noticed like usually after like flatten, I'd have like 400,000 parameters or something like that. Whereas for this, I could get it down to 15,000 parameters.
Okay, interesting. How did it? Okay, what optimizer did you use? That's strange. I don't think
Atom,
I've
I
ever
believe.
seen. I don't think I've ever seen pooling being used in the middle of the dense part of the network. But that's really interesting. How did it work on your accuracy if it's down there below?
Yeah. Well, so I think this model is slightly different than the one that's in the actual file. This one has a much lower false negative, but
Mhm.
has a higher false positive, whereas the
Right.
other one was like the other way around. And yeah, so the loss over here was like significantly higher than on the training data, so I think it might have overfit a little bit.
Mhm. Good analysis of your own model's performance. Should I go ahead and run it on the full data set, or do you like definitively know that it's not the same model?
Yeah, I know it's not the same model, but like it's close enough. It should be fine.
All right, so I can go ahead and run it.
Yeah.
Thank you for sharing. Let's change it to Group 5's copy. Let it get evaluated. That's interesting. So what pooling does is it kind of abstracts the data into like a simpler thing to process by taking the max of a certain set of values at a time. And next week we'll actually like explain to you a step further about how like convolutional neural networks work, because we just said don't worry about this, don't worry about that, you just write this part, and it's just kind of like super abstract at the moment. But for your knowledge and for you to be able to relate things better, we will be talking about how convolutional neural nets work. Okay, so the loss here was 0.13. We seem to have quite a few false negatives. Not that many, but quite a few. And that seems to have come out of true positives. So, okay, so your precision is really high, right? And that's because your false positive rate was like pretty low. So your precision score was really high, but when it came to recall, it's not that, like none of these models so far are by any means bad. They're all like really good. And in the industry, anything above an 80% accuracy is definitely production ready. So there's no like downplaying of your achievements in these scores. But your model seems to be tilted towards precision as opposed to recall. Cool. Any questions, or shall we move to where's We have group 6 is the last model. If we have anyone from group 6 today, I think we do. All right, let's move to group 6. Who wants to present?
I guess I can. So our model currently, I'm restarting the run because I just did a run on it, and I have a similar issue to one of the other groups where we had a model that was working, but like right now it's like the thing shut down. Like you were in there, you were in our breakout room, like when
Right.
you did. So I'm not sure what happened there.
So was it failing to save, or because
Yeah,
it did get saved? At least some version of it got saved here.
all right. Yeah, because like right after we ran it, and it was like at, if I remember correctly, it was like at 93%. I think double checked it and said it was saved. Maybe, I don't know. Maybe the previous version got saved instead. So I'm currently like rerunning it to see like if it works, because
Right.
I think something like that happened last time.
Cool.
So,
Once
should I
you,
share my screen?
yeah. Go ahead.
All right. Here, one sec. There. So yeah, right now, as you see, I'm currently like running the thing. So I guess I'll start with the, what you call it,
The model.
right here.
Right.
Oh, yeah. That's what it was. We had more neurons. We had a lot more neurons.
I see.
Yep, it didn't save the amount of neurons we used. Oof. Yeah.
All right, well, let's see how this version does.
Oh, this version should be around 50%.
Okay.
Yeah, because we had lots of more neurons. Like I think if I remember correctly, like this one might have been in like the hundreds. This one lower than that, and then this might have stayed 4 actually. But like these two were definitely different.
Right, and that's usually a trend in most neural networks that are pretty deep. We like to have more neurons in the start and the middle, and as we get closer to the end, we like to reduce the complexity by reducing the number of neurons so that it gets easier to classify it in the end.
Yep. And for the optimizer, we did use Atom.
Adam, okay.
All right. So, yeah.
Right. One thing about these, the default learning rates have been set to a pretty good level by the folks at Keras, because they've done a ton of testing, and they've seen that 0.001, which is the learning rate on most of these, the default value of the learning rate, it works really well for most problems. So
should I just stop sharing?
Yeah, sure.
Or should I?
I'm not sure which version is here, but I can go ahead and run it.
Yeah, that'd be cool. Yeah.
Right.
Hopefully it's the good one.
Let's see. Forgot the jazz. So nice. I might actually use this somewhere. Wait, is this my good bot? Oh no, this is my terrible one. Oh wait, okay. I believe I saved this with my name. Okay, I'm gonna run this after this one finishes.
How does it not break with like that many parameters?
That's what, first of all, you're using the GPU, right? So it is able to perform that many computations without too much of a hassle. But on data from like the industry, we don't deal with data in terms of thousands. We deal with data from like 4 to 5 million examples. And like that's called big data. And when we have to deal with that, training times are huge because of how long it takes to work with that level of data. But parameters wise, it's capable of performing those computations. Just don't run it on your local machine because that's gonna, the only thing it'll be good for is making pancakes. All right, let's see. Oh wow, okay, all your numbers are like 95 or up, so maybe this is a slightly different version. But that's totally cool. And those are the models that we have today. If anyone didn't get their model saved, I am happy to help. Like I said, today's meeting isn't as long, but I will show you my own bot. Hang on. All right. Where is it? So I had a ton of neurons. 500, and then I brought it down to 200, and then 100, and then this is standard. So as you can see, it's quite a lot of parameters, but do not let parameters alone define whether your model is a good model or not. I remember someone, I think Vivek mentioned adding max pooling to reduce the number of parameters. That's usually good, but beyond a point, it starts to abstract things more than necessary. I think yours was fine, and I've never seen max pooling used in between dense layers. That's just maybe my inexperience with that, but more parameters isn't always a bad thing. It's just make sure you have the computational capability of a GPU or something more. Right, so I used RMS prop. Let's see how my model does. I'm pretty sure it's not the best model that was here today in terms of recall, which is our defining metric for the day. Mine isn't as solid, but I think it was sufficient. You guys are now welcome. I know like while you guys were working on this, we didn't let you change the number of epochs, but if you want, go home and I mean, you guys are home. Stay home and try to change the number of epochs to see if 5 is too many. Maybe it could have learned the same amount with 3, or maybe 5 is too few and it could do better with way more. And we can give you this file as well so you can test it on shuffle data. Right. So as you can see, quite a few false negatives, false positives, but I think I already ran this at the start, but yeah, my recall is like 94-ish. But good stuff, guys. Great work on your projects. If anyone has any questions or concerns or bugs, we are ready to help you out. Otherwise, if you have nothing to talk about and stuff, you're free to go. Oh, and next week we're going to be talking about like I mentioned this, right? But we're going to be talking a little bit more in depth about stuff that we said you can ignore in the current version of the project. We're going to walk you through a few more concepts.
For like actually training the model, is there a way to bake in like the idea that a false negative is worse than a false positive? Mm-hmm. Or is it kind of just whatever? Like, can you add like weight to false negatives more than false positives somehow?
I believe there is a version of the F1 score which adds weight. It doesn't directly add weight to the false negative, false positive, but it can add a weight to the concerned entity. And that's called the weighted F1 score. This gets pretty detailed into statistics, but it can be fun. But by nature, because of the variables that precision takes into account and recall takes into account, you're intentionally leaving out stuff that is irrelevant. So you're sort of weighting it by putting it into the formula to get precision or recall. I think I can stop recording, right?